What's up, everybody? Mr. McCarson here with another video on measurement and calculation. This time we're on part 5. We just got done doing a lab in class, and one of the areas that we have to talk about in this lab at the end of it was we have to talk about error in our laboratory measurements, and then we have to talk about how to calculate percent error based on the actual values that we measure in class with our lab partners versus the theoretical values, which are the values that are the accepted correct answer. So join me as we cover these two topics, and thank you for being here. All right, so the first topic we're going to talk about is error. Now, to be very clear, error is something that is always going to occur in any laboratory experiment, whether it's a beginner lab in a high school chemistry class or working in a professional pharmaceutical lab. Error can absolutely be minimized, especially given the experience of the scientists and their talent and skill working within a specific discipline, and also the equipment. The nicer, more high dollar, very sophisticated equipment tends to help minimize error. But make no mistake, error is going to occur in all labs across the earth that humans partake in and even beyond. It's usually unavoidable. Our goal is always to minimize error that occurs in our laboratory experiments. And you can still do a really good job with simple tools and simple procedures and techniques as long as you care and you're worried about accuracy and precision in your measurements. So let's define error. Error is the difference in your actual lab value that you measure with your lab partners in class when compared to the established correct value. Okay, so let's add a couple of definitions there. The first is the accepted value. Okay, the accepted value is the right answer. Now, how do we know accepted values? They're based on reliable references. So, for example, if you go to ptable.com, it's a really nice online interactive periodic table. They will have the accepted densities of all of the elements on the periodic table, and you can look them up and change the units for them. Where that information comes from is decades upon decades of very high degree accuracy and precision measurements on density and consensus by the highest groups of chemists and physicists that work together in professional and university settings. And so we've collected that data. So there are definitely sets of data where we consider them the accepted values. Okay. Now, the experimental value is what you get in lab. So whenever you are given, for example, a density lab and you and your partners are going to calculate the density of copper, you're going to come up, when you use the technique in class, with your own actual value for the density of copper. Then you're going to look up on a set data table that is accepted as a reliable source the accepted value of the density of copper, and then you can subtract those two and find the difference to get your error. So error, mathematically, is the experimental value minus or take away the accepted value. Now, a big thing about error is it can be negative. And if your error is a negative value, all that means is your accepted value was greater than your experimental. So your experimental was a little bit underneath where the accepted was supposed to be. Okay, so it's okay if you have a negative value for error, and it's okay if you have a positive value for error. All that tells you is the difference of whether your experimental was below or above the accepted. Okay, so very wordy, but here's our definition for percent error. So first off, percent error is calculated by taking the absolute value of the experimental value minus the accepted value. So we figure that out, the error. We take the absolute value of the error, then we divide this difference by the accepted value again, and finally we take that overall quotient and we multiply this by 100 to convert it to a percent. Okay, now the purpose, why do we do this? The purpose of this calculation is to let a scientist know how effective their lab technique, procedure, or skill is at determining the correct outcome. It lets you know if you're doing it well. Okay, as a teacher, when I look at percent error, if I see a low percent error, and I know that it's not attributable to something like luck, It tells me that you did the technique well. You measured carefully. You were very, very accurate and precise if you're doing things multiple times with your data, and that you were able to follow the procedure that I laid out for you in lab correctly. Okay, so it's a way that we can use to grade, if you will, your overall lab technique. Now, in higher level courses, like if you go to some universities, they will actually, in like Chem 101 lab, they will actually look at your percent error as part of your grade. Okay, so percent error is an important calculation. You want to be honest with it, especially at the high school level. Like in my classes, the expectation is you're honest. And if it's bad, if your percent error is really high, it shows you that you're making mistakes. The importance of that is to understand where you're making them so that when you get to university settings or professional settings, you don't make them. Remember, you can make mistakes in a high school chemistry class. When you're working in a pharmaceutical lab on an important medication that humans will take with consequence, you want to minimize that error. Okay, so very important to understand the definition of percent error and the reasoning behind it. All right, so let's get to the good stuff. So here's our formula for percent error. This is definitely something, if you're in my class, you want to write down somewhere until you either memorize or you're very comfortable with it. But percent error is equal to what we call the absolute value. So these are absolute value bars, meaning that even if your error is negative, you're still going to make it positive. So the absolute value of the error, which is the experimental value, take away the accepted value. And then what we're going to do is we're going to take that difference and divide it by the accepted value. Now, once we get this outcome, once we get this quotient, we're going to multiply that by 100%, and that will become our percent error. So an example of a problem where you might be required to use the percent error formula says this: I know that I weigh 150 kilograms. If I weigh myself and the balance says 165, what is the percent error? In this case, what is the error built into the balance? Like, how far is it off? Now, knowing that I weigh 150 kilograms, that would be something that comes from a balance that is reliable. So maybe the balance that you step on at your doctor's office, like when I go to Kaiser, they have this really fancy balance, and I'm sure it's very expensive, and it's to many decimal places showing me my mass or my weight in kilograms. So I kind of trust that's the accepted. And then my scale at home from Target, which is much cheaper, is going to be close to that. It might be over, it might be lower. I hope it's a little bit lower sometimes, you know what I mean? But I can figure out percent error from those two values, okay? So once again, if we say it one more time, percent error equals the absolute value of your experimental minus your accepted values, all divided by your accepted value times 100. And once again, that is to convert it to a percent. Okay, so let's use this in a couple examples. All right, so let's go ahead and now try to calculate from our last example. Let's actually go ahead and put this into practice. So once again, our problem says I know that I weigh 150 kilograms. If I weigh myself and the balance says 165 kilograms, what is the percent error of the balance? So percent error equals the absolute value of the experimental value minus the accepted value. We call that the error, divided by the accepted value times 100. So if we want to show the math to plug this in, here's how it would look. And my absolute value bars are a little bit off, so I apologize for that. They should be up a little bit higher. But the percent error equals the absolute value of 165 minus 150 kilograms, all divided by 150 kilograms times 100. Now, when we break that down even further here, it's going to be 15 kilograms divided by 150 kilograms. 15 kilograms is the absolute value of the error. And then we multiply by 100. Now, when we work this math out in our calculator, it comes out to be a 10% error. Now, 10% is not insignificant. That's a pretty significant error in a lab. In college, that would probably cost you points. In high school, it's not great. It lets you know that there was something wrong in your procedure or your technique or your skill using a particular tool. Something didn't go perfect, and that's normal, but we want to try to stay at like maybe 5% or less is a decent percent error for what we're doing in high school labs. And obviously, the further up you go to the higher stakes science situations, you want to really minimize that error. Like for some labs, I mean, a 1% error is a bad thing if you're talking about creating medication that will reach millions of people. You don't want to have that much error. So it really depends on the situation, but in general, like 10% is not great, right? 10% is not great. Now, a real quick note on sig figs. The sig figs that we're really counting for this come from the experimental value and the accepted value. We look at those for sig figs. So like 15 is 2 sig figs, and 150, the way it's written, is 2 sig figs. So we want 2 sig figs in our percent error. The 100% doesn't count for that. That's kind of a definition of how we convert to percents. So we look at it almost like a conversion. We don't really count that for percent error. So just a quick note on how sig figs work. And once again, we're not going to be overly concerned there. Do the best you can with it, looking at the sig figs in the experimental and accepted values to work the sig figs for how you round your final percent error for labs. All right, so let's set up another practice problem. Here it says we want to find the percent error in a length measurement of 4.25 centimeters if the correct value is 4.08 centimeters. So we were given something where the actual value with a tool of a high degree of confidence was 4.08 centimeters. When we measured it with our tool in class in lab, we got 4.25 centimeters. So 4.25, this would be considered, right? This would be considered our experimental. So that's our experimental value. Okay, why is it the experimental? Because it's what we got in class when we did it in lab with our own hands, with our partners. The accepted value is 4.08. So this is the accepted value. Okay, so the accepted value, remember, is what we determine as correct. So we have the accepted value or the correct value in the experimental. So when we set up, we always do the experimental minus the accepted, and we do the absolute value of that difference. So here it's 4.25, take away 4.08. And then we divide all of that by the accepted value again. So here, if we look at it, what you get for the absolute value of the error is 0.17 centimeters all over 4.08 centimeters. Now, when we analyze this for sig figs, we have 2 sig figs in the numerator and 3 in the denominator. And the rules of sig figs for dividing say you go to the fewest sig figs, so that's going to be 2. So when we take this quotient and we multiply by 100%, it rounds to 4.2% error, which is pretty good. That's a much more acceptable. Like you're moderately happy with that percent error if you're in my class. All right, last example for this video, and then we'll practice some more in class, so please feel free to ask questions in class. It says, what is the correct percent error for a mass measurement of 17.76 grams, given that the correct value is 21.2 grams? So once again, when we're given percent error, we have to identify 2 factors. What was the experimental value and what was the accepted? Now, the experimental is 17.76. That's what we were figuring out and we measured in lab. And then the accepted value is 21.2. Why? Because they said it's the correct value. So the correct value is known as the accepted value. So we go ahead and plug those in to our formula. The absolute value of the experimental minus the accepted. Okay, so we got experimental minus the accepted, and we always take the absolute value of that. Okay, divided again or all over the accepted, so 21.2. Now what happens is the absolute value of our error is 3.44, okay? And then we're going to divide that by 21.2. And if we notice, both of these have 3 significant figures. And when we take this and multiply by 100, we're going to get a final percent error of 16.2% once it's rounded. Not great. Like I said, this is now for high school even, we start to look at this and go, okay, what are the problems? Was it a pouring? Was it measuring? Was it obviously if we're working with mass here in grams, was there something wrong with our balance? Did we not zero out the weigh tray? Once you see the percent error is really high, the goal as a beginning chemistry student is to start to reassess your technique, your materials, your tools, what procedure you went through. Okay, so I hope this helped. Once again, percent error equals the absolute value of the experimental value minus the accepted value, all divided by the accepted value, multiplied by 100. And we're going to keep it 100, and I'll see you on the next video. Have a good one. Bye.